So much of what we do in introductory level physics is going to be working with physical quantities that can be represented one of two ways. So either these are things that are going to be what are known as scalars, or they're quantities that can be represented by vectors. So for starters, what distinguishes between these two? Well, for a scalar, the only thing that matters is its magnitude. Effectively, a scalar is just a number. We'll run into scalars that can be positive, scalars that can be negative, but the only thing that matters for a scalar is just its magnitude. Vectors, on the other hand, we care about both the magnitude and direction of a vector. So a vector will have some length, plus it will also point in a particular direction. So if we want to think about some physical quantities that are represented by these two things, well, there's a lot of them that we already know. So if we think about some scalars, so things like time, distance, speed, mass, these are quantities that you already know, have a good sense of what those are, but they're all scalars, right? The only thing that matters is the amount. Density, energy, power, work, heat. So all of these are words that you've probably heard before. They have specific meanings that we'll use in talking about them in physics. But the important detail here is just remembering that these are all scalars. They're numbers, and so we get to treat them as numbers. Vectors, on the other hand, again, we care about both magnitude and direction. And so there are a lot of physical quantities that we're going to deal with throughout both this class and the second semester course that are going to be represented by vectors. So position, where something is located, cares about not just how far away from some point is it, but in what direction do you have to go to get there. Again, displacement, that's a vector. It's going to care about you were here when you started, you were there when you ended up, and so I can figure out what the distance between those two is, right? But that distance is a scalar. The displacement also cares about, well, in what direction do you have to travel a certain distance. Again, these next two, speed, the scalar, is just how fast are you going. Velocity, the vector, is how fast are you traveling and in what direction. Acceleration, that's a vector. Force is a vector. What we'll see is that force and momentum, acceleration, these things are all related to each other. Then we'll come back and talk about torque and angular momentum and how they're related to each other. And in the end, the last vector quantity that we'll care about, particularly if you end up taking the second semester of the class, is a field. So all these are vectors. Part of why we care so much about scalars versus vectors is the fact that you can sort of fundamentally break down the introductory level course to working one of two problems. You're either going to be working this scalar problem that often deals with things like work and energy. So the names that we're going to give to our scalar problems are using the work-energy theorem, solving for something using conservation of energy. Our thermodynamics problems are almost always scalar problems. Again, scalar problems for us will tend to be keeping track of what's going on with energy. Our vector problems, on the other hand, we're going to see that most of our vector problems are going to build off of Newton's laws. So whether we're doing the dynamics piece of Newton's second law or the kinematics, whether we come back and think about momentum, which is really what Newton's laws are telling us about, all of those are just different ways of framing this particular vector problem that we're going to work over and over and over again throughout the semester. So it would be hard for me to overstate this, but what we're going to do is basically through this sequence work two problems. Scalar problems that typically keep track of energy, vector problems that typically keep track of forces and momentum. And so the first thing we want to make sure that we really understand is how these two things are different so we can recognize which type of problem we need to work. Alright, so we've said that a vector is a quantity that has both a magnitude and a direction. Again, for this class, we're going to deal almost exclusively with vectors that are in two-dimensional space. So things that can be represented in the xy plane. So here's vector A. I notice that it points along the x-axis in the positive x direction. And so there's a couple things just notationally we want to make sure are clear up front. So for any vector, if we write it as A with the vector symbol on top, we're talking about vector A. If we write it A with the vector symbol on top, but then the two straight lines on the outside, basically in the same way that we would think about the absolute value of a quantity, that's one way that we can talk about the magnitude of vector A. The other way is just to drop the vector symbol. So either of these, and we'll go back and forth in using them, so just make sure you're comfortable with that, but either of these are ways that we'll talk about the magnitude of vector A. How long is that vector? What we'll also talk about are the components of a vector. So you see A with an x subscript, A with a y subscript. The x subscript says I want the x component of vector A. The y subscript says I want the y component of vector A. What is worth going ahead and pointing out, the components ax and ay are scalars. They're just numbers. They can be positive, they can be negative, they can be zero. It's when I put them together in a special way that I get a vector. Okay? So notice there's no vector notation. That vector symbol is not sitting above the components because the components themselves are scalars. When I put that vector symbol on there, there's no x or y or even z, right? So just make sure that if you've got the vector symbol, you're talking about the vector. If you have x or y, you're talking about the component. That's not a vector anymore. One way that I can describe a vector is to report its magnitude and its direction. And what we'll see is there's a couple of easy ways for us to do that. One is simply just telling you how long the vector is and in which direction it points. So here I might say that vector A happens to have a magnitude of 12 meters and points in the positive x direction. Vector B has a magnitude of 15 meters, so notice B is a little bit longer than A, and it points in negative y. Vector C has a magnitude of 20 meters and points at an angle 35 degrees above the positive x-axis. So all of these are simply ways of telling you what vectors A, B, and C are by telling you A, their magnitude, and B, their direction. Now, of course, here I'm giving you the directions relative to x and y as coordinates. We'll also work problems where we could deal with cardinal directions. So north, south, east, west, but it's the same thing. So here, now instead of having plus x and plus y delineating the x and y axes, what I've got is I'm telling you I've got a vector A that has a magnitude of 12 meters and points due east. Vector B has a magnitude of 15 meters and points due south. Vector C has a magnitude of 20 meters and points 35 degrees north of east. So notice in terms of dealing with this particular description, you basically sort of read it backwards. Start east, turn 35 degrees north of that. So 35 degrees north of east is an angle made relative to the east direction. This picture then is, you can think of this as sort of like looking down on a map. We sort of have an overhead view that we're looking down on our vectors now, but we're still using them to describe both a magnitude and a direction.